Alright, so this is our first video for chapter 15. So we're going to deal with the electrostatic force. So that is the force between two charged particles. First we're going to look at our classical atomic model. And so you may have seen this in your earlier science classes, and maybe in chemistry you talk about a different, more refined model where electrons are quantized wave functions, and they inhabit orbitals and things of that nature. But we're just going to start with the classical model of the atom. So we know it consists of positive charges, negative charges, and our non-charged particles, our neutrons. So we're gonna focus on our protons and our electrons. So our convention is we call electrons negatively charged, protons are positively charged. That's really just arbitrary. That's our convention. That's just kind of the assignment we gave them when prior to their discovery. So we know that an atom, in general, an atom will have a dense nucleus, very small in diameter, and then it's surrounded by, we'll call it like an electron cloud or something like that, right? And so the electrons are, not necessarily behaving as particles, but they're, orbiting the nucleus. So we're going to assign this property that charged particles have. This property that charged particles have, we're going to give it the SI unit of the Coulomb. Okay, it's the Coulomb, capital C. So that was named after Charles Coulomb, who actually discovered the electrostatic force, which we'll talk about later. So protons and electrons are both massive, and they have equal and opposite charges. Right? So they have the same magnitude of charge, but their sign is opposite, right? So we give the proton a plus sign, right, because it's positively charged, and then the electron is negatively charged, so it's got a negative sign. The fundamental unit of charge is 1.6 times 10 to the negative 19 coulombs. So we're going to be using that number quite often in the next couple chapters. All right, so this is just this is a value that's handy to have close by. So a proton and an electron have the same magnitude of charge. The signs are opposite. The proton is much more massive than the electron. All right, the proton is 1.67 times 10 to the negative 27 kilograms. All right, in chem class you probably use a more convenient units to describe the mass or the weight of these particles. The electron is much less massive, 9.11 times 10 to the negative 31 kilograms. So the fundamental unit of charge and these two masses are, again, they're quantities that we're going to be using fairly often in the next couple chapters, so again, they're good to have handy. And we're in physics class, so it can be kind of annoying, but we want to be in kilograms for our masses. So every macroscopic object, what do I mean? Every large object has a net charge Q. Okay, and the net charge, so we're going to use this variable for the amount of charge that some large object has. So it's the fundamental unit of charge times the number of protons, right, positive, minus the fundamental unit of charge times the number of electrons, right? So it's fundamental unit of charge times the difference between the number of protons and the number of electrons. So in general, if you're just walking around your house or whatever, most of your objects that are just sitting there are electrically neutral, right? So they're not full of like charged particles, right? They have a bunch of protons, have a bunch of electrons, but in general they're electrically neutral. But we're going to be dealing with objects that are charged, right? So they're going to have a charge Q in coulombs, right? Because remember, this is in coulombs. These are just numbers, right? So these are unitless. Okay, so Q has SI unit of coulombs as well. So this is called charge quantization, right? We don't have, we aren't going to be dealing with fractions of the fundamental unit of charge, right? So we're at least going to have charges of that magnitude. So it's possible for an atom to gain an electron or lose an electron. So when an atom loses an electron, it has more protons than electrons, so it becomes ionized. That's what we call a positive ion. So this has a net positive charge. Okay, if we go back to this formula, and if we found out how many protons, how many electrons it has, this number would be positive. So it would have a net positive charge of 1e, right? So it would basically act as though it was a proton, right? Because all the negative and positive charges are canceling each other out, with the exception of the extra proton, right? So this will behave. It's much more massive, but it will behave as one proton. Similarly over here, right? If we gain an electron, we have one more electron than we have protons, so the net charge would be negative, right? This number would be negative, and its charge would be negative e. Right? So this, concerning the charge, it would act as though it's just one positive electron. So that's ionization. So we're going to be dealing largely with conductors. We're going to be dealing largely with conductors. The reason we do that is because electrons are weakly bound to the nuclei in conductors. Most of the time we're going to be dealing with metals, right? Metals are very efficient conductors. So the outer electrons in every atom, they're weakly bound to their respective nucleus. So it doesn't take a whole lot of force, which we'll be dealing with later. It doesn't take a whole lot of force or a whole lot of work for those valence electrons or valence electrons, however you want to pronounce it, for those outer electrons to be removed from their atom and then basically be free electrons, right? So every atom is either, depending on the metal, it's either contributing one or two free electrons into this metal, right? Or this, we call it a sea of electrons. Right, so it's kind of like a soup inside the metal where you have a bunch of free electrons. Whereas in an insulator, the valence electrons are very tightly bound to the nuclei, so you can conduct electricity through some insulators, but it's very, very difficult. It takes a very large force to do it. And then there are consequences to it, right? When you're trying to move electrons through an insulator, you also heat it up too. So you get a lot of problems with that. So we deal with conductors primarily, especially when we get into like chapter 17 and chapter 18, when we start talking about electrons flowing through a wire. We're going to be dealing with metal wires because it's much easier for these valence electrons to be free and move through the metal. So we're going to talk about Coulomb's law. This was discovered by Charles Coulomb, a French general, I believe. I don't know what his rank was, but he was an engineer for the French military, and he did physics experiments, and he discovered that similar charges are going to repel each other, and then like charges are going to attract each other. But he wanted to formalize this, and you'll see some parallels. In 120, you may have seen Newton's law of universal gravitation, and I'll show you that formula later on. But Newton's law of universal gravitation, if let's say you take the Earth and the Moon, they're two massive objects, and they are applying forces on each other, and that's a gravitational force. It's a long-range force, and it's an attractive force. So the Moon and Earth are applying attractive forces on each other. So this law says that it's directly proportional to the masses of those two objects. Right? So it's directly proportional to the mass of the Earth times the mass of the Moon. And it's inversely proportional to the square of the distance between them. So the farther two massive objects are away from each other, the smaller the gravitational force is that those two objects are exerting on each other. Okay, so the closer they are, the stronger it is. The more massive they are, the stronger it is, and then the farther apart they are, the weaker it is. So Coulomb's law, this is the electrostatic force, behaves very similarly. So it's going to be inversely proportional to the distance between them, but it's going to be directly proportional to how much charge these two macroscopic objects possess. Right? So it's going to be proportional to the charges of the two objects, and it's going to be inversely proportional to the square of the distance between them. And we'll see the formula on the next slide. But so we give in our diagrams, the plus sign means they're positively charged, the negative signs means they're negatively charged. So these are like charged particles, and they are repelling each other. Right? This is a third law pair. This is a Newton's third law pair. These forces are equal in magnitude and opposite in direction, and they're the same type of force. Okay, so Q2 is exerting a force on Q1, Q1 is exerting a force on Q2. So it doesn't matter if they're both positive or if they're both negative. If they're the same charge, it's a repulsive force. So if they were oppositely charged particles, the force would be attractive. Right? They'd be pulling the other charge towards them. Still a third law pair. Still the same relationship, proportional to the charges, inversely proportional to the distance between them. So it's not a constant force. Right? In 120 we dealt with the constant force pretty often. This is not a constant force. Right? So the closer these two get, the stronger that force is going to be. Okay. And so here's our formula. It does look very similar to Newton's law of universal gravitation. So what we have to recognize here is that this force is a vector, so it's got magnitude and direction. This version of Coulomb's law just can only be used to calculate the magnitude of the force between these two particles. So you notice that even though these could both be negative, or one could be negative, both could be positive, we're disregarding the signs of the actual charges when we're calculating the magnitude. But because the force is a vector, we're going to use our vector mathematics to determine the direction and this relationship, right? The fact that it's repulsive between positive charges and attractive, or excuse me, repulsive between the same charges and then attractive between opposite charges. Right? So we have to keep that in mind when we're trying to find the direction of a force exerted on a particle. Okay. So K is, some people refer to it as Coulomb's constant or the electrostatic constant. It's much like that capital G, the universal gravitational constant in Newton's law. But this capital K is the electrostatic constant, and it's 9 times 10 to the 9 Newton meters squared per Coulomb squared. Right? So the reason it has these units is because force is in newtons, so we want the meter squared in the denominator to go away, so that would cancel. And then we want the coulombs to go away up here, so there's a coulomb squared in the denominator, meter squared in the numerator, and we're left with newtons. Okay, and so what I'll do is when I do my examples, I put the units in there. I try to be a good physics person and put my units in there, and then I'll cancel it out and I'll show you that we're left with newtons. So we'll do a basic one-dimensional Coulomb's law force. We're just going to use Coulomb's law. It's going to be much like a 120 problem. We're going to do a free body diagram, use Newton's second law, and find something out about this problem. So we have an electron which is released from a certain height above the Earth's surface. We don't know what that is. There's a second electron directly below it that's exerting the electrostatic force on that electron above it. And that force, it says it's just great enough to cancel the gravitational force on it. So the gravitational force on an electron is very weak because the particle is not very massive, right? So we've got a very, very small mass. So it's a weak gravitational force, and we're looking for the distance between these two particles, right? So there's an electron above another electron. They're exerting an electrostatic force on each other, and we want to know the distance between them. So I'm going to start with a free body diagram, and this is my electron. It's some distance from the surface of the Earth, and for these purposes I just put the electron on the surface of the Earth, right? So we're looking for this distance, right? How far above this electron is the top, or is, the electron above it? So we know these are both electrons, so they are exerting repulsive forces on each other. Okay, so this electron is exerting a force down on this electron. This electron is exerting a force in the positive y direction on this electron. But the electron is near the surface of the Earth, so it is experiencing a gravitational force in the negative y direction. So it's a nice one-dimensional Newton's law problem, Newton's second law problem. We know the charge, right? The charge for an electron is negative 1.6 times 10 to the negative 19 coulombs. So charge is a scalar, but it can be positive or negative depending on the charge on the particle, right? So we have to be mindful of that. We know the mass of the electron. I'm going to write Newton's second law in the y direction, and I'm setting it equal to 0 because the problem said that the electric force on the first electron is great enough to cancel the gravitational force. So the net force in the y direction is 0. So that means the electric force minus the gravitational force is 0. So that means they're equal to each other. So that makes sense, right? The electric force is canceling out the gravitational force. They're equal to each other. So from 120, we know the gravitational force is the mass of the particle times the acceleration due to gravity. And I use Coulomb's law here. Notice Q1 and Q2, they're in, we use absolute value bars, right? So the sign doesn't matter. The force is a vector. We're just looking at the magnitude of the electric force. So Coulomb's law for the electric force, mg for the gravitational force. So now it's time for our algebra, because what am I looking for? I'm looking for the distance between these two particles, right? I called it h in my diagram, but I know it's r. I know it's the distance between the two particles. So I have to solve for r. So I'm going to multiply both sides by r squared, divide both sides by mg. So now I have r squared by itself. Take the square root of both sides. Once you take the square root of both sides, you get the square root of k times the product of the two charges divided by mg. So now I'm ready to plug everything in. I know my electrostatic constant, and notice they're in absolute value bars. So these are the charges of the electrons, but again, I'm only concerned with their magnitude here. Okay, so I'm not using any negative signs here. Divided by the mass of the electron times the acceleration due to gravity. So what I like to do here, so depending on what kind of calculator you have, we're dealing with very, very small numbers and very, very large numbers. And so what I like to do, it takes a little bit of time, but it helps me avoid making calculator mistakes. So I'm taking all my coefficients, right? I'm taking my 9, my 1.6, my 1.6, my 9.11, my 9.8, and I'm factoring them all out, or I'm grouping them all together, right? So there's my 9, my 1.6, my 1.6, my 9.11, my 9.8. Then all my powers of 10, I'm leaving them out. Okay, so I got 10 to the 9, 10 to the negative 19, 10 to the negative 19, and in my denominator I've got 10 to the negative 31. So the reason I'm doing this is because I'm going to use my exponent rules to simplify all these powers of 10, and then I'll just use my calculator for these constants over here. Okay, so 10 to the 9th times 10 to the negative 19 times 10 to the negative 19 is 10 to the negative 29, right? So we've got the same base. I'm multiplying terms that have the same base, I'm adding the powers together. Right? So 9 minus 19 minus 19 is negative 29. So in my denominator, I still have 10 to the negative 31. I calculate all this stuff, I've got 23.04 in the numerator, 89.29 in the denominator. So this right here, another exponent rule, I'm dividing, so I'm actually subtracting a negative 31 from negative 29. Or you could bring this up and make it positive, and then I'm adding 31 to 29, which is 10 squared. Okay. So again, this might be, you know, a little annoying to you, but I find it easier to do this in most cases because I want to avoid calculator mistakes, you know, because I'm dealing with a lot of large powers of 10. So this right here, this number right here is 0.26, and I've got 10 squared. So don't forget, I'm taking the square root of all this, right? This is still under the radical. So when I calculate this, I get a distance of 5.1 meters, right? So the top electron is 5.1 meters above the bottom electron. So how do I know I'm in meters? Okay, so I took all my units out and I just kind of solved for them separately, right? So my electrostatic constant, I've got Newton meters squared per coulomb squared. I've got coulombs times coulombs for the charges, kilograms for the mass, meters per second squared for the acceleration due to gravity. So from 120, F net equals mass times acceleration, right? So a Newton is a kilogram meter per second squared. I've got a Newton in the numerator, and in my denominator I've got kilogram meters per second squared. These coulombs cancel out with this one, and I'm left with just meters squared under the radical. And the square root of meter squared is meters. So it's helpful to put units in. You know, I know we tend to kind of, you know, get lazy. I'm certainly guilty of it. Just kind of throw our numbers in there and stuff. But it helps to have our units just so we can kind of make sure we're doing our algebra correctly and we're solving for the quantity that's being asked. All right, so I've got two spheres, and they're of equal mass, 0.2 grams. So they're suspended by strings. Right? So these are two strings. If you remember from 120, a string has a tension in it. So each one of these particles is experiencing a tension force from the string. So the spheres are given the same charge. I don't see any signs on here, so I don't know what I'm going to do about that. Are they positively charged, negatively charged? I don't know. Keep reading the problem. The spheres are given the same charge. Come to equilibrium. Okay, so both the spheres are at rest right now. So they're suspended in the air. They're at rest. So that means the acceleration is not zero, or the acceleration zero. So the net force on each one of these spheres is zero. At an angle of theta equals 5 degrees. Okay, so there's theta, and 5 degrees is also here. Right, so that's 5 degrees, that's 5 degrees. The string is 30 centimeters long. What's the magnitude of the charge on each sphere? So I'm feeling pretty good because it's just asking me for the magnitude of the charge. Right, so I guess I'll deal with, you know, whether they're positive or negative later. Maybe I won't have to, right? So I'm going to pick one of these particles. So if you notice, they are both suspended by a string the same length, right? So they're exerting forces on each other, and they're probably on planet Earth, so they're experiencing a gravitational force too. So if I draw a free body diagram for this one, it's just a mirror image of a free body diagram for that one. So here's my free body diagram. I've got the mass, right? I converted grams to kilograms. Don't forget to do that. I converted grams to kilograms. I've got the mass of the sphere. I've got the length of the string, which I converted to meters. This angle right here was theta, and I'm looking for the charge. Okay. So here's my free body diagram. So the tension is acting in this direction. The gravitational force is acting in the negative y direction. The electric force on the sphere on the left is in the negative x direction. How did I determine that? They're given the same charge, right? I don't know if it's positive, I don't know if it's negative, but they're given the same charge. So that means they're like charges, so they are exerting repulsive forces on each other. Right? So this charge is pushing this one away, this one is pushing this charge away. So I know the electric force, it's repulsive, so it's in the negative x direction. The whole system is at equilibrium, so the net force in the x direction is 0, and the net force in the y direction is 0. So I don't like this angle. Right? If I go back here, right, I don't like this theta. I don't like this 5 degrees, because the tension is acting in that direction. Okay, going back to my 120 vector mathematics stuff, I want this angle right here. I like the angle to be measured from the nearest x-axis. Okay, so what I have to do is I'm going to take this right triangle right here, and then this is 5 degrees. This angle right here has to be theta's complement, because it's a right triangle, right? So these two angles have to add up to 90. So I want this angle. I'm going to call it phi, and this angle here is 85 degrees. It's the complement of 5 degrees. So that's the angle I'm going to use when I'm describing my tension force vector. So I write Newton's second law in the x direction. Newton's second law in the x direction is the x component of the tension force, T cosine theta, minus the electric force. And it's equal to 0, because it's at equilibrium. F net in the y direction, the sine component, or the vertical component of the tension force, is acting in the positive y direction, so it's T sine theta, and then the gravitational force is acting in the negative y direction, so it's it's T sine phi minus the gravitational force. Again, equilibrium, F net in the y direction also equal to 0. So I'm going to substitute Coulomb's law in here for the electrostatic force, add that to both sides, and then I'll add the mass times acceleration due to gravity in here for the gravitational force, add that to both sides, and I've got these two equations right here. So that's very nice. So I'm being asked for the charge, Q1 or Q2. Now these are the same. So I'm going to rewrite that as Q squared in a minute. So I'm looking for that, right? So I've got a system, right? I'm looking for Q. I've got T. That's two variables. I got a problem, right? I've got R squared that I don't know. So I'll have to find that. So for now, I'm just going to solve both of these equations for T and then set them equal to each other, right? So if I solve this for T and I solve this for T, whatever's equal to T, those are equivalent expressions. Okay, those are equivalent expressions, so I'm allowed to set them equal to each other. So this equation right here, I divide both sides by cosine phi. This right here, I divide both sides by sine phi. And then I have this, right? So I'm solving them both for T and setting them equal to each other. So Q1 is equal to Q2. Are they positive? Are they negative? I don't know. All I know is they're the same, and I'm being asked for the magnitude. So I don't have to worry about whether they're positive or negative. That's good. So Q1 times Q2 is just going to be Q squared. So I can substitute Q squared in for this, right? And then we can solve for Q, right? Divide both sides by K, multiply both sides by this denominator, R squared cosine phi, and I've got this expression for Q squared. Take the square root of both sides. Cosine phi over sine phi is cotangent phi. So I was trying to clean the problem up, and then I went to my $100 calculator and realized I don't have cotangent function on it, so kind of useless, but whatever, it looks nice. I'm still going to have to evaluate cosine phi over sine phi. Maybe there's a cotangent function hidden in my fancy calculator somewhere, I don't know. So I've got a nice expression for Q, but I still need R. Right? I still need R. So I'm going to come up here and then back to my diagram. R is the straight line distance between these two particles. It's a straight line distance between these two particles. But I don't know what that is. But when I was looking for this angle that I wanted, this angle phi, I drew a right triangle with a hypotenuse that was equal to the length of the string. So now I've got this angle. I've also got this angle, which I could still use, but I've got this angle phi, and I've got the hypotenuse of this right triangle. Now the base of this right triangle is half the distance between these two particles. So it's r over 2. So I've got a right triangle whose hypotenuse I know both the interior angles, and I know the base is equal to half the distance between the particles, which is what I'm looking for. So what trig function would you like to use? I want to use phi because I have the adjacent side and the hypotenuse. So I'm going to write cosine phi is equal to the adjacent side, r over 2, divided by the hypotenuse, which is L. So I know phi, I know L, I can use this to solve for R. Multiply both sides by L, multiply both sides by 2, I get R is 2L cosine phi. Substitute my values in, don't forget this is in meters, so 2 times 0.3 meters times a cosine of 85 degrees, and I get 0.05 meters. Don't forget, make sure your calculator's in degree mode. We still want to be in degree mode. So the distance, notice I solve for R, not R over 2. The distance between the two spheres is 0.05 meters. So now that I have that, I can plug everything in. I've got the mass of the sphere, acceleration due to gravity, just found R, cotangent of 85, divided by Coulomb's constant, and I get the magnitude of the charge Q. 7 times 10 to the negative 9 coulombs, or as we'll see in a lot of example problems, 10 to the negative 9 is nanocoulombs. Okay, so we're going to see microcoulombs and nanocoulombs very often. Okay, so if you ever see this, it's 10 to the negative 9. Okay. We'll do one more problem, and I think I'll stop. I always try to stop at 30 minutes. That ends up being like 45 minutes. If you know me, I'm pretty long-winded, so I try not to be with these videos. So I'm going to do this problem. I'll pause it, and then I'll finish up my examples in a second video. So this is a common problem. I'm pretty sure you'll see this on a WebAssign problem. So I've got two charges, and if you don't have a diagram, the problem will tell you what the sign of the charges is. Okay, so this 6 nanocoulomb charge is positive. Right? It doesn't have a sign next to it, so I'm going to assume it's positive. And then another charge of 3 nanocoulombs, which is negative. So I've got a positive and a negative charge that are separated by a distance of 60 centimeters. So I know that they're going to attract each other, right? But we'll just say for the time being they're at fixed locations and they can't move. So I want to find where I can put a 12 nanocoulomb charge in this region so that the net force on it is 0. So I'm going to treat this as a one-dimensional problem. So let's say they're all 3 of these charges are fixed on some horizontal axis. Okay, so I'll put the positive charge over here, and I'll put the negative charge over here. They're separated by a distance of 0.6 meters. So in one dimension, there are 3 possible regions where I could put this 12 nanocoulomb charge. So I could put it to the left of the 6, I could put it in between the 6 and the negative 3, and I could put it to the right of the 3. So that sounds like a lot of work, right? There are a lot of different regions where I could put this 12 nanocoulomb charge. So I want to try to eliminate some of those regions that are impossible. So what I did was I drew free body diagrams for the 12 nanocoulomb charge in all 3 of these regions. So region A, that's to the left of the 6 nanocoulomb charge. If I was a positive charge over here, the 6 nanocoulomb charge would push me away, and the negative 3 nanocoulomb charge would attract me. So I'm feeling pretty good about this free body diagram, right? Because I want the net force to be 0, so that means these two forces have to be in opposite directions. Okay, so I'm feeling pretty good about region A. That's a possibility. Let's check out region B. If I'm a positive charge here, the 6 nanocoulomb charge is going to push me in the positive x direction, and the negative 3 nanocoulomb charge is going to pull me in the same direction. So if I'm in region B, both of the forces due to these particles are going to be acting in the same direction. So there's no way I can put the charge there in region B. And it would be the same for a negative charge, right? The charges, or the forces, would just act in the negative x direction. So we can't write an equation that cancels these forces out and matches our free body diagram. So I just canceled out region B. So that's great. Region C, the same thing happens. Right, if I'm over here, I'm going to experience a repulsive force here, and I'm going to experience an attractive force due to the 3 nanocoulomb charge. So these are opposite directions. This is a possibility. Okay. So only one of these actually works. And spoiler alert, it's region C. And I'll show you why it's region C. So I'm setting these two electrostatic forces on, or I'm setting them equal to each other. And then I'm trying to find this distance x, right? How far away from this 6 nanocoulomb charge do I have to be? So I've got Coulomb's law on the left side, Coulomb's law on the right side. My distances are different, right? So my subscripts are okay, right? Q6, Q12, right? That's the force of the 6 on the 12. Q3, Q12, that's the force of the 3 on the 12. So K cancels out, right? This is an equation, right? K cancels, Q12 cancels. What about these distances? What's going on with these distances? So this is the distance between the 6 nanocoulomb charge and the 12 nanocoulomb charge, which I'm calling x. Okay, not too bad, right? X squared looks good. Now, over here, the force by the 3 on the 12, what's the distance between these two particles? The distance between the 3 nanocoulomb charge and wherever I'm going to put the 12 nanocoulomb charge is this whole distance, 0.6 meters, plus x. All right, so watch out for that. So you're a different distance from this one than you are from this one. Okay, so that's where we get these denominators right here. So what else goes away? All right, we canceled out the Q12s, we canceled out the Ks. We can plug our values for the charges in there, right? We know these two charges, and we're just looking for x. So it looks like something I can solve, right? One equation, one variable. So 6 nanocoulombs, 3 nanocoulombs. Again, don't forget this is magnitude, so I don't have a sign here. Okay. So the 10 to the negative 9 coulombs cancel out. I have 6 over x squared equals 3 over 0.6 plus x squared. Okay. So what else? Oh, I can divide 3 out. That's good, right? So 6 and 3. Also, I cross multiplied here, right? So this came up here. This x squared came over here. So I've got 2 times the quantity 0.6 plus x squared equals x squared. I don't want to factor this out because it'll look like it'll look like a quadratic, and maybe the terms will go away and maybe I won't have to factor it again or something like that. But what I notice is I can take the square root of both sides instead, right? So instead of like factoring this out, distributing the 2, making it messy, I can just take the square root of both sides. So square root of 2, square root of this term is just 0.6 plus x, square root of x squared is just x. So I got rid of all my quadratic terms. It's a linear equation. Now I can distribute that root 2, and root 2 times 0.6 is 0.84. I converted that to a truncated decimal 1.4 just for calculation purposes. So I've got a 1.4x here, I've got an x on this side, subtract 1.4x from both sides, I get negative 0.4x is 0.84. And so when I solve for this distance, I get negative 2.1 meters. So you might be thinking, all right, that's not that bad, you know, a negative, I'm on the left, I'm in the negative x direction. Here's the problem. If we look at Coulomb's law, okay, this particle has a greater charge than this particle, right? The magnitude of this charge is greater than the magnitude of this charge. So the force on Q12 by Q6 is going to be greater, right? Q6 times Q12 is greater than Q3 times Q12. Also, if I'm over here, I'm always going to be closer to the 6 nanocoulomb charge than I am the negative 3 nanocoulomb charge. So it's the force by the 6 nanocoulomb charge on the 12 nanocoulomb charge is greater because their charges are greater, and it's greater because they're closer to each other. So that's why we got our negative distance, right? So this force is always going to be larger than this force. So region A can't happen. Sorry people, we did all that work for nothing. But now we can recognize, right, if we have a situation similar to this, we can disregard this region. If you're closer to a particle with more charge, that force is going to be greater, right? Those forces are going to be greater, okay? So this force is always greater than this force in this case, right? For a positive particle, this is positive, this is negative. That may switch, right? Your Webb assign this might be positive, that's negative. It might be, you know, where do you put a negative charge or something like that. So you have to recognize that one side is going to be off limits for this reason, because one of those forces is always going to be greater. Okay. So if you can recognize that before going through all this and getting a negative distance, that'll help you. So region A is a no-go, region B is a no-go. It's got to be region C, or hopefully it's not one of those physics problems that, you know, messes with you and gives you, you know, no real solution. But I think we'll be okay over here. So I'm going to call this distance y, and I'm setting it up the same way, right? The only difference is the distances are going to change, right? So the force by the 6 nanocoulomb charge on the 12 nanocoulomb charge is K, Q6, Q12, but now we've got a new distance. I'm over on this side. What's the distance between where I'm going to put the 12 nanocoulomb charge and the 6 nanocoulomb charge? It's 0.6 meters plus y. So I'm farther away from the 6 than I am the 3, right? Which is contrary to what was happening in region A, which is good. So the distance between the 6 and the 12 is 0.6 plus y, the quantity squared. I'm closer to the 3 nanocoulomb charge. So K, Q3, Q12, the distance between the 3 and the 12 is just y. And so the fact that these denominators are switched, right, that should give me a positive y value. So we plug everything in. Well, let's get rid of our Q12s like we did before, right? Q12s go away, the K goes away. Let's see, I have 6 nanocoulombs, 3 nanocoulombs, the nanos go away, the coulombs go away. I can factor out a 2, divide both sides, or factor out a 3, divide both sides by 3. Right? So I've got a 2 over here, I got a 1 over here. So again, I got one equation, one variable. Now I'm solving for y. I cross multiply, so I got 2y squared is the quantity 0.6 plus y squared. I'm going to do the same thing, algebra wise, take the square root of both sides. Root 2y is 0.6 plus y. Right? So I don't factor this out and, you know, try and make it look like a quadratic or anything. So root 2y is 0.6 plus y. Root 2 is, you know, roughly 1.4. So I'm going to subtract a y from both sides. 1.4 minus 1 is 0.4. And I have 0.6 on the right side. Divide both sides by 0.4. and I get a positive y value, so that's good, right? So I have to be, the only place that this 12 nanocoulomb charge can be is 1.5 meters to the right of the -3 nanocoulomb charge. So again, now region C makes sense because you're closer to this to the 3 nanocoulomb charge, which is smaller than the 6 nanocoulomb charge. So even though this charge is greater, you're closer to the 3 nanocoulomb charge. Okay, so this denominator is greater for the 6 nanocoulomb charge, so this force is smaller. Okay, so it's larger because of the charges, but it's smaller because of the distance between them, which was different over here because this force is always going to be larger than this. But there is a location in region C where these forces cancel out, and that's what we were looking for. Okay, so I'm going to stop this, encode it, upload it, do everything I got to do, get it on YouTube, and get the link on D2L, and I will pick up with the last couple topics in chapter 15. Okay, thanks.